So how'd the concentration profile go for others? How far along did we get? Yeah, go ahead. Feel free to start doodling if you'd like. Did anyone have any specific difficulties? Equilibrium definitely sounds like one, so I would agree there. Set this up. And let's also define the domain. So let's start by labeling our axes if we can. Yeah. Good. CA is a function of R.
Hey, I was about to come in there with that time arrow. It's validating to see somebody with the time arrow in the same direction as me.
I like the group effort on it. You know, it's a crowdsourcing. Good. Somebody picked up on what I wanted, a vertical line indicating the domain. Good, good, good. And thank you for labeling what's on the inside and what's on the outside. So I'm going to start with the first case, which is the intraparticle diffusion control. That's what's labeled on the top. And I'm going to start just like I would on the exam and start labeling. So CA is the concentration of species A on the vertical axis. Good. The horizontal axis is distance R, with the domain from 0 to big R indicating the internal pill, and from big R to infinity indicating the fluid around the pill. So that's everything out here. In this case, there's a line drawn, a horizontal line at CA infinity, which tells me that the concentration in the fluid around the pill is well mixed. So the concentration is a very low concentration, so low that presumably it's 0 around the pill. And the inside of the pill has a gradient, and as time goes on, the concentration is going down. There are two boundary conditions that you need to satisfy on the inside of the pill. One is in the center and the other is on the outer wall. What I see here at the center is a symmetry boundary condition. So presumably all of these have a slope of 0, which I agree. However, anyone have a thought about this concentration profile? Or any alternate ideas on how this might look, specifically with time?
I don't exactly understand the question. Are you saying if this was just in terms of time versus?
Nope. Somebody caught on. So the original drawing over here had all the concentrations starting at the same location. This would indicate that as time goes on, the middle of the pill never changes in concentration.
Oh.
But I think what's actually happening is what's drawn in blue. As time goes on, the concentration in the middle is going down. The slope is always still 0, so it's still symmetrical. You have symmetry boundary condition there, but it's going down.
But then over at the end, it's all converging because that's where it's all going to a nullified concentration.
Yes, exactly. So this over here is the second boundary condition, which is actually your constant concentration boundary condition. So you know the inside of the pill has to be in equilibrium with the outside. The outside has a constant concentration, so the pill has to have a constant concentration over there. Okay, so I completely agree with this blue curve going down. There's one final point that I see is missing over here, and I'm gonna clean up some things. So let's see if this works for me. Just to clean that up a little. If I were to zoom in down here, what does this look like? And I think somebody drew in green 2 dots. I'm going to agree. I think that, and I'm just gonna redraw this. There should be equilibrium at the interface. Yes, thank you. Somebody's adding it in. So the CAS is a constant value. Let's say it'll look, as time goes on, you end up with something like this. and it always goes to that constant CAS value. And that CAS value is in equilibrium in accordance with this relationship right here. So the surface concentration on the pill side has to be greater than the surface concentration on the liquid side, the fluid side, because S is a positive number greater than 1. So that means the pill side has a higher concentration than the liquid side, so that dot has to be greater than. Okay, good. I think this pretty much gets it there. Let me think. If I want to be nitpicky, we need to define some of the other given information like CI. The initial concentration was given in the problem statement. So that CI should be given there. What else? C infinity was given, which is great. And we have to be careful. It's not actually CA infinity. What was given in the problem was just called C infinity. So we have to just be careful. And C infinity, I guess if you're going based on what was on the previous slide, was given to be 0. But in this case, it also would hold true if it was a non-zero number. Any questions about the intraparticle solution over here? And I would exaggerate this equilibrium too, just to make it very clear that these aren't the same location.